The flocking modifier is a bit different than the other modifiers, in that the falloff value here drives a simulation, while the falloff value in most of the other modifiers is used to directly modify or transform an instance. The flocking modifier is a pretty one-to-one implementation of a paper that's known as Boids today, just as a side note for you tech-savvy guys out there. So how do you set this up? Well, let's start with a platonic. And I'm already within a geometry here. Let's orient it along the z-axis. All our individual voids, that means our swarm particles, are oriented along their z-axis. Next, let's drop down an instancer. And in here, create an instance geometry and link it up with the platonic here. By the way, some of you guys complained that you cannot see which geometry goes into the instancer. And as a visual hint, you can go to View, and then Dependency Links, Show for Selected Nodes, or Show for all nodes. So Houdini will display those kind of lines showing which geometry is being used in the instancer. For now, I will just hide those. Okay, let's set our instancer's distribution to spherical and highlight it. Also, under instancing, we maybe want to scale down our individual particles here and scale them a bit along the z-axis so we can see which way they are pointing. Also, let's increase their number to maybe 250. 200. Next, let's use a plane falloff in this case, and just set it to 1, so each individual void will have a falloff of 1, and thus will be fully active. Finally, let's drop down the flocking modifier. Wire it up, highlight it, and you can immediately see the individual instances' orientation changing. And that is due to the fact that flocking orients the instances towards the direction of their movement, that is their velocity. Let's just check the real-time toggle and hit play here. And we can see those swarming around. Let's hit stop again, zoom a bit out, maybe increase our number of frames. And let's go over the settings. So flocking, or Boids, tries to balance several forces in a particle system, which in the end will result in a swarm-like behavior. On the one hand, what you can do is reset the whole simulation, so if for some reason your simulation won't update, just reset it. You can see simulation caches just got erased and you can resim. So these are your kind of standard simulation caching setups. Let's scroll down a bit. So these are all of our current Boid settings, and these are the individual forces that act on each of those individual particles here. The first one is the urge to be driven to the center of mass of the whole swarm. In this case, it would be the center of that sphere at the first frame. And this is the weight. So this is just a multiplier that's being used to weigh this strength of the force that pulls those individual particles to the center. Next, each particle tries to avoid particles around itself. On the one hand, the repulsion weight drives how strong the overall effect of that force on the overall particle system is. Then, this is the distance in which the particle system looks for other particles around one given particle. So let's increase that a bit. And you can already see those particles get affected a bit stronger because now even particles that are further away from each other get pushed apart a bit. And you'd have to adjust this repulsion distance according to the scale of your individual particles so that it doesn't intersect with other particles. Also, here's the angle of influence. So when you look at the direction in which the particles are moving, the way my particle system is set up now, each particle will only look for colliding particles in front of it in an angle of 180 degrees. So you can expand or kind of narrow the view angle in which each particle looks out for different, possibly colliding particles. The next force driving the particle system is the urge to match the velocities of surrounding particles. So again, the match velocity slider is just the strength of that force, and then the distance and angle of influence, in the same manner as with the avoidance here, is driving how the particle system finds other particles around each individual particle that it then tries to match in velocity. That means in speed and direction. Then we have an option to add some curl noise in, which by default is set to 0 because it's not in the original Boids paper. However, it adds a bit of a natural motion here, so maybe you want to dial it up to 0.05, 0.1, something like that. Next, we have the ability to clamp the velocity, because our Boids, when we look at them as physical creatures, fish or birds, they cannot have an infinitely high velocity. Birds won't go supersonic, so that's why you clamp them usually. Otherwise, the behavior gets a bit weird. And you have to adjust this, because sometimes your particle system moves a bit faster or wants to move a bit faster and cannot match its target. So you have to increase the velocity here or give the particle system a bit more time to reach its target. Speaking about target, finally, you have the option to use a target, which your particle system extracts from a spline that you feed in there. And again, this is the overall strength of that force pulling our particles to that target, and this is the position of the target on a given spline, ranging from 0, the start of a spline, to 1, the end of the spline. To demonstrate, let's just go into the top view by hitting space and 2, zoom out a bit, and then drop down a curve. And with the tool handle selected, let's draw a cheap curve, starting around the beginning, and then just maybe going like this here, hit enter. You just drop down a curve. Let's resample that, set it to a subdivision curve, wire this in, so we have this smooth curve here, and that goes into the second input of our flocking, where it says guide spline. Okay, back to our perspective view, and now what I want to do, I want to animate the target position, ranging from 0 on the first frame to, maybe let's go to, frame 300, and set its target position to 1 there. Also set a keyframe by alt-clicking in there, and go back. In the MOPS flocking, let's hit Reset Simulation, and click Play. So not much happening there. That is because I have to increase the follow target strength as well. And this one is really, really sensitive. So you'll have to dial this in really, really carefully. So let's try a value of 0.005 to start and hit play. And we can see the swarm is already following that spline. However, it's clumping together here. That is because the strength of the force pulling those individual particles to the target position on that spline is too strong. So either what we could do is dial down the follow target strength at the risk of those particles not moving towards the target position on the spline quickly enough. The other thing that we could do is increase the avoidance strength. Play again. Nope, that's still clumping up. And after a bit of fiddling around with the parameters, I found that the maximum velocity was set too low, so the particles could not move as fast as they would like to actually avoid each other colliding. So if we set this to 0.3, now the particles are allowed to actually move faster and have a bit more chance of moving away from each other. So hit play again. We can see on the one hand the particles move a bit quicker, on the other hand they do not clump up as quickly. Also, let's maybe mix in a bit of curl noise. Let's try a strength of 0.1. Maybe a bit too strong, so let's try 0.05 instead. Yeah, I like that better. And again, this is a really sensitive system. And finally, one setting we haven't mentioned yet is the use falloff checkbox. What that does is it takes this strength value and multiplies it with the falloff. So a falloff of 1 will just say all those forces are not scaled down. A falloff of 0, however, means do not use that force at all. So once we set MOPS plane falloff to 0, we can see now that our particles aren't moving at all, because all of the forces are scaled down to 0. Let's maybe add a random falloff value using the randomize node like this. Highlight flocking again and hit play, so you might be able to see how strongly individual copies with individual falloff values are affected by the Boyd's behavior. And you can see those Boyds with the really low falloff value, the blue ones, move kind of slower and not as coherent as the rest, which exhibits a more stronger flocking behavior. So that is MOPS flocking. Again, a really basic implementation of the original paper, which results in some of those values being overly sensitive, so you have to be really careful when dialing them in. However, once you got your behavior figured out and the whole behavior of a system, it's kind of a fun one, because using those simple rules, it's still able to simulate very natural, very organic, and sometimes very complex behavior. So that's the flocking modifier.